This video is going to go over the AP Calculus AB free response question number 2 from the 2008 Form B exam. They haven't done Form B exams in a number of years, but it's a problem that I like from a couple years back. And really the whole key to this problem is units, just units and reading carefully. They give us this story about R of t is the speed in kilometers per hour. Liters of gasoline used to travel x kilometers is modeled by g of x. How many kilometers does the car travel during the first 2 hours? Well, the first function that they give us here, r of t, is kilometers per hour. That's the rate of change of kilometers. And if you have the rate of change of something and you want to know the net change of that, so how fast is kilometers changing? How many kilometers? I just take an antiderivative, in particular a definite integral on a given interval. So part A, and this is calculator allowed, so that's super nice. Whoa, we do not need a giant pen stroke like that. A little something smaller here. Part A is just the definite integral from 0 to 2 of r of t dt, which my calculator tells me is 206.37 kilometers. Part B, find the rate of change with respect to time of the number of liters of gasoline used by the car when t equals 2. So what we're looking for here in part B is we're looking for dg dt when t equals 2. That's the question we're trying to answer. Now we have two functions. This function r is a rate, but it's not the rate we're looking for. It's the rate of change of kilometers per hour. And kilometers is given to us as x here, which is weird that this is r of t, but rate, I guess. But really I think they're just trying to make you think a little bit more deeply about your units and your letters. This r of t is the rate of change of kilometers per hour. It's really, r of t is really dx dt, because x represents kilometers in g, in the equation g. So r of t is really dx dt. G is not a rate. It's just the number of liters of gasoline used. But if I were to take the derivative, then g prime would represent the rate of change of liters of gas per kilometer, because x is the input here. So what we have to recognize is that what we want is dg dt. I'm given dx dt. I can very easily find dg dx. Neither of those are the rate of change that I want. But if I multiply these two things together, the dx dt in the numerator here and the dx in the numerator here will cancel out, leaving me just the dt. The dx in the denominator here will cancel out, leaving me just the dg in the numerator. So that will give me what I want if I multiply these things. So let's do that. So dg dt, which is what I'm trying to figure out, is going to equal dg dx times dx dt. Now we're doing this when t is equal to 2. And remember that dx dt is just r of t. So to figure this out, when t is 2, we just need to plug in 2 to r of t here. So that's easy enough. So this thing here becomes r of 2, which is 120. Just plug 2 into that expression on your calculator. The dg dx, first of all, we need to take the derivative of g, and then we have to plug in x to that. And that's where this one is really sneaky, because you can't, if you take the derivative here, don't find g prime of 2. 2 is a number of hours. You need to put in a number of kilometers here. Now, how many kilometers do you need to put in? Well, isn't that nice? The question in A asked us to figure that out. How many kilometers does the car travel in the first 2 hours? So what I need here for my dg dx is g prime, not of 2, but of 206.37. Then I'm going to multiply those things together. Again, because this is a calculator allowed question, I would just do this g prime of 206.37 on my calculator, math 8 for most of us with the TI-84 series, rather than writing out the whole chain product rule with a chain rule inside of it and plugging in this fairly ugly decimal. And when I do that on my calculator, I got 0.05. And then we multiply these things together, and we should get 6. And that, in terms of units, because we're looking for the rate of change with respect to time, the number of liters of gas when the car has traveled 2 hours, this would be liters per hour. So a really sneaky one with units there in part B. Really got to figure out, okay, what rate of change am I really dealing with? And then this 206 that you have to plug in there is extra sneaky. But again, that's because the question is asking when t equals 2, but there's no t in this equation. So you have to figure out what's the corresponding x value when t equals 2, and that's your answer for part A, because x is kilometers, and that is kilometers at 2. Part C has some more unit fun here. How many liters of gasoline have been used by the car when it reaches a speed of 80 kilometers per hour? Well, they want to know how many liters of gas. So I would like to just be able to plug in some value of x to g. But x represents the number of kilometers driven. What they gave me was a rate. So I have a function for the rate. So what I have to do for part C is first set r of t equal to 80. When I set that equal to 80, again, it's calculator allowed, you're going to get approximately 0.33145. And you can do that many ways on your calculator to solve that. You can, show the work, do the algebra, and just get that natural log on your calculator. Or you can use your graph, whatever is best for you to solve that. But it's r of t equals 80. Now, I'm still not ready to plug that into g to figure out the number of liters of gas, because g has an input that is x, which is kilometers. This is now hours. We went from a rate to an hour. So I need to figure out how many kilometers have I gone at this time. Well, that's the same work that we did in part A. So I need to then figure out what's the definite integral from 0 to 0.33145 of r of t. Certainly doing that on my calculator. When I do that, I get 10.794 approximately. That is a number of kilometers, so that can go into g. So I need g of 10.794. When I do that on my calculator, I get 0.537 liters. So a tricky one just because of how many units you've got to keep straight and deal with here. For the most part, you're just going from a rate to the net change, like in part A, or doing a little bit of finding a derivative at a particular point. But it's dealing with the units that make this one particularly challenging.